Let's look at this next example. In this next example, they've asked us to find C positive such that the area of the region enclosed by the parabolas y equals x squared minus c squared and y equals c squared minus x squared equals 10. So in this case, they've given us the answer, and we have to come up with the exact functions so that the area between them will equal 10. So how do we do this? Well, we can't graph them because we don't know the value of c at this point. But what we can do is sketch them. So what does y equals x squared minus c squared look like if c is positive? Well, we know that first the y equals x squared, a standard parabola, looks like this. And if c squared will be positive, and we're subtracting that, then that will shift this down so that y equals x squared minus c squared will look like the parabola, but below, with the vertex below the x-axis. Similarly, if we want to look at y equals c squared minus x squared, we just start with the graph of y equals minus x squared, which is the parabola upside down with its vertex on the origin. And now we're adding c squared to that, and that will move it up so that y equals c squared minus x squared will look something like this. And what they're asking us to do is to find these values here of x so that this entire region is equal to 10. So now let's find these points of intersection, and they're going to be in terms of c, by setting x squared minus c squared equal to c squared minus x squared. So now adding x squared to over here, we'll have 2x squared, and adding c squared to the right hand side will have equals 2c squared. So in other words, x squared equals c squared, so x is going to equal plus or minus c. So here, since c is positive, this will have an x value of negative c, and this point will have an x value of c. So those are going to be the bounds of integration that we're going to use. So now let's set up the integral. So what we're going to be doing is we're going to be integrating between minus c and c, and the graph on top, this is going to be the c squared minus x squared, minus the graph that represents the lower portion of the region, and that will be x squared minus c squared, making sure that we put that in parentheses with respect to x. And we know that we need this result to equal 10. So we need to find the value of c that will make this happen. Now we can make this a little bit simpler if we recognize that the region is symmetric about the y-axis. So what we can do is integrate from 0 to c, and that result should equal 5 by symmetry. So from 0 to c, c squared minus x squared minus the x squared minus c squared should equal 5. And that will be a little bit more simple to calculate. So now let's go ahead and work out this integral here, remembering that c squared is just a constant. So simplifying this down, we'll have the integral between 0 and c of 2c squared minus 2x squared, just distributing the negative sign and combining terms. And now when we integrate, well, the integral of 2c squared, which is a constant with respect to x, will just be 2c squared x. And the integral of minus 2x squared is going to be, with respect to x, we'll have minus 2/3 x cubed. And all of this evaluated between 0 and c has to equal 5. So now we're going to use the fundamental theorem of calculus. We put in c for x, and we'll have 2c cubed minus 2/3 c cubed. minus, and this is the fundamental theorem of calculus, and now if we put in 0 for x into both terms, we just get 0, and that has to equal 5. So we need to find the value of c that will make this equal to 5. So if we combine these two, we're going to have 4/3 c cubed equal to 5, or c cubed equal to 15/4. So c is going to equal the cube root of 15/4. So if we take c to be the cube root of 15/4, then this entire region here will equal 10. And we could check our answer if we put the cube root of 15/4 in for c and calculated the area of the region. And we should